Before we get started, if you haven't subscribed to the channel, please consider subscribing.
Here we will take a look at how to estimate Tobit models and also how to write custom functions to maximize the log likelihood using R. And for this, I'm going to solve this particular problem step by step for the different parts and show the R script to do this solution. Okay, so here's my R script. I'll go through this as we go through each of the parts step by step. So the first part here is it's asking us to simulate a sample size of n equals to 1000 to generate data for y star, which is equals to 1 plus beta naught times x plus ui, where ui conditional on xi is distributed normally with mean 0 variance 2, and then yi itself is equals to yi star times the indicator variable where yi star is positive. So here, for simplicity, we assume that the intercept in the yi star equation and the variance are unknown. The parameters to be estimated below is beta naught. So what we are interested in estimating is the coefficient beta 0 or beta naught. When we simulate the data, we set beta naught equals to 0.5, so we set its true value equals to 0.5, and our objective is to get an estimate of that. We generate the x size as uniform, so the variable x is drawn from a uniform distribution on 0, 1. Okay, and we'll be setting c equals to 42 for reproducibility. Okay, so the first part that we need to do is we need to generate the data, and then we need to see what fraction of the observations in the sample are actually censored. Censored meaning what fraction of the observations in the data, in this case, are positive, right? Okay, let's see. So we set up the R environment and set up the seed, set up the number of observations, preliminary steps, and then we generate the independent variable from a uniform distribution. So R unif, which is the draw of random from a uniform distribution, sample size is n, which is 1000, the lower bound is 0, upper bound is 1. All right, and then we generate the errors from a normal distribution with mean 0 and variance 2. So this is random, and then the next part is normal. So our norm, sample size n, mean 0, standard deviation is square root of 2. So the argument that goes in this command is standard deviation. So hence we are using the SD equals to square root of the variance 2. Next, we generate the yi star variable where the true beta naught value is set as 0.5. So this is very simply this equation 1 plus 0.5 times x plus ui, which is exactly what we do here. Next, we generate the yi variable, and y observed is equals to if else y is greater than 0, y or else 0. So basically, whenever y is taking a positive value, we are keeping that value of y, and otherwise, which is else, we are just setting it 0. So this is making the sample censored. So we only have observations for positive y's, and we only have zeros for y's where it's not positive. Now we look at the fraction of censored observation. So basically we take the sum, or we basically take the count of the number of observations where y is equals to 0 divided by the total number of observation n, which is 1000 here, and we can see that almost 19.6% of the observations are censored in this random sample. So we are ready with the dataset for our Tobit simulation. Next step, let's take a look. So next step of the problem is to construct a custom R function that, given the data, computes the log likelihood of the model in part B evaluated at beta. So we need to write a custom function to compute the log likelihood of the model. All right, let's see. First step, L is equals to, so we start with some object L that is going to be our container for some results. So we have n number, so n number is 1000 here, so we have 1000 zeros stored, repeated in this object L. Next, sigma squared s equals to 2, okay, and define a function to calculate the log likelihood, okay. Initialize a loop to iterate over each observation. So we are going to, the function that we are writing is going to take each observation from the sample and then do the calculations, okay. So function, the arguments or the inputs are the dependent variable, independent variables, and then the value of beta. The loop starts with as a for loop for I in 1 to length of y. So this is going to take total number of observations. And then if yi is not equals to 0, so if the observation is not censored, in that case L for that particular iteration I is equals to d norm, which is calculating the normal density function value, where the mean is given by 1 plus beta times x, which is the model that we started with here, and the standard deviation is the square root of s, which is the variance 2 that we had initially set. Calculate the normal density function value. This is being done using d norm, and then we take the natural log of the density. If the observation is censored, which we are doing with the else branch of the loop, then we calculate the cumulative normal distribution function using the p norm, okay. So this is the PDF and this is the CDF. All right, so using the p norm we do the CDF and we have the same mean for the model, same standard deviation, and then we take the natural log of the CDF. Finally, we do the log likelihood, which is the sum of L. So for each observation we have a likelihood number that we just calculated using either p norm or d norm. So we are summing them across all the observations, and then we are taking an average of them. So this is 1 by n times the summation of the log of the likelihood function or the formula. And then we are returning that as the final output of the function that we are writing. Now let's get into part C, which is asking us to plot the log likelihood of the data generated in part A against the values of beta in a grid of points from -3 to +3. And then it's asking us to compute the grid search version of the maximum likelihood estimator of beta. So it's asking us to search within this grid of -3 to +3 with a step size of 0.1 to see which one would be the most optimal beta within this grid. And then it's asking us to mark the true value and the estimated value on a graph. All right. So first we set up the grid, which is a sequence of numbers from -3 to +3 by step size 0.01. All right, and then we create an object to store the results, which we call grid_log L, and then we get the log likelihoods of the values. So remember, we have already defined this custom function log likelihood. We just start a loop using for I in 1 to length of the grid. So the number of iterations that we have here, for each iteration we run the log likelihood function and we store it. Okay, and we can see we have a red line and a green line, right? So they're very, very close. So that's great. So the grid search is very close to the true value, and that's because the grid that we considered indeed contains the true value, and we can see how the log likelihood is increasing and then it's decreasing. So this is a well-behaved function, so we can basically maximize this and pinpoint the optimal log likelihood, the maximum log likelihood point, and the beta that maximizes the log likelihood. And that is what we'll be doing in the last part of this video, which is part D. Part D is asking us to use the optimize function in R to numerically maximize the log likelihood function defined in part B, and then to report that MLE estimate of beta. So this is what we'll be doing ideally, or this is what any canned package does for us when we ask it to do a maximum likelihood estimation. So first we define the optimization function. So we are writing our own custom function to optimize. So function, its inputs are y and x. And then first object here is this optimize function. So we are using the optimize function to maximize the log likelihood over the interval -3 to +3. We pass the log likelihood function, the interval and the data to the optimizer, and we set maximum equals to true to find the maximum of the log likelihood, or the maximum of whatever function we basically insert here in this argument. And then it returns the optimal beta value, which is the first element of the optimization result. And remember, the way we set up our custom function log likelihood, it has 3 inputs, y, x, and beta. And in this case, we are already feeding in 2 inputs, y and x, but we are not feeding in any input for the variable beta. So that is exactly what this function is going to solve for and then return. If we had more than one variables that were not set, then it would solve, or it would try to solve for all of them, and then it would return a list of those variables if it can solve for them. So that's how the optimize function works. Anyways, moving to this part, we see that the maximum that it has estimated is 0.46, or if we round it up to 2 digits, it's 0.47. That's very, very close to the true value of 0.5 that we set at the beginning. I'm pretty confident that if we increase the sample size further, this would keep getting closer and closer to the true value of 0.5. So I'll do a different video for part E, which is a Monte Carlo simulation for the Tobit model. But basically, in summary, this is exactly how we can write our own custom functions, and we can do Tobit models in R, and we can also estimate the log likelihood by maximizing the likelihood function in R.
If you like my videos and find them helpful, then please support my work by subscribing to the channel.